Imagine a place in the cosmos so extreme, so bizarre, that it bends the very fabric of reality. A place where gravity is so powerful that nothing, not even light, can escape its grasp. This is a black hole. It is not a hole in the traditional sense, but rather an immense amount of matter squeezed into an impossibly small space. Think of the sun, with all its mass, crushed down to the size of a city. The result is a gravitational field so intense that it creates a one-way door in the universe. Once you cross its boundary, known as the event horizon, there is no turning back. Your journey ends at a point of infinite density called a singularity, where our known laws of physics simply break down. The universe loves to hide its greatest secrets in the most challenging of places, and black holes are the ultimate cosmic puzzle box. They are born from the explosive deaths of massive stars, their collapsed cores leaving behind these gravitational ghosts. Or they can be supermassive, lurking at the centers of galaxies, including our own Milky Way, like cosmic puppet masters orchestrating the dance of stars around them. For decades, they were purely theoretical, predictions of Einstein's general theory of relativity. They were mathematical curiosities, too strange to be real. But the universe is often stranger than we can imagine, and the quest to understand them pushes us to the very limits of our knowledge. What makes them so compelling is that they are laboratories for the extreme. They are where space and time become distorted in ways we struggle to comprehend. Inside a black hole, time and space can switch roles. The future becomes a physical destination, the singularity, that you are inevitably pulled toward, just as we are all pulled toward tomorrow. This is where the two great pillars of modern physics, general relativity and quantum mechanics, collide. To truly understand a black hole, we need a new kind of physics, a new way of seeing the cosmos. They are not just objects, they are questions posed by the universe itself. Exploring black holes is a journey into the unknown. It is a story of human curiosity and our relentless drive to make sense of the cosmos we inhabit. They represent the frontier of astrophysics, a place where every new observation has the potential to rewrite our textbooks. They challenge our intuition and inspire awe. They remind us that there are still fundamental mysteries out there, waiting to be solved. And as we peel back their layers, we learn not just about them, but about the fundamental nature of space, time, gravity, and our own place within this grand cosmic drama. The universe is speaking to us, and black holes are one of its most profound languages. For a long time, the idea of taking a picture of a black hole seemed like an impossible dream. How do you photograph something that absorbs all light? You don't. You photograph its shadow. You look for the silhouette it casts against the glowing, superheated material swirling around it. This was the monumental task of the Event Horizon Telescope, a global network of radio telescopes all working together, synchronized by atomic clocks, to create a virtual observatory the size of our planet. Their goal was to achieve the resolution needed to capture an image of the event horizon of a black hole for the very first time. It was an audacious plan, a testament to human ingenuity and collaboration. And in 2019, they did it. The world saw the first direct image of a black hole, M87 star, located 55 million light-years away at the heart of the Messier 87 galaxy. It was a breathtaking sight. A dark central region, the black hole's shadow, surrounded by a blazing, lopsided ring of light. That light is from gas and dust heated to billions of degrees, moving at nearly the speed of light as it spirals into oblivion. This image was not just a picture, it was a confirmation. It was a stunning vindication of Einstein's theories, showing us that these exotic objects are real and look just as relativity predicted they would. We had finally seen the unseeable. The Event Horizon Telescope collaboration did not stop there. A few years later, they gave us a portrait of the black hole at the center of our own galaxy, Sagittarius A star. And now, with even more powerful observations, scientists are seeing these cosmic engines in unprecedented detail. They are mapping the magnetic fields that thread through the accretion disk, the swirling platter of material feeding the beast. These magnetic fields are thought to be the architects of the colossal jets of particles that some black holes launch into space. These jets can be larger than the galaxies they come from, shaping the evolution of stars and gas on a cosmic scale. By studying these images and the data behind them, we are no longer just theorizing. We are observing. We are watching matter in its final moments before it crosses the point of no return. We are seeing how black holes feed and how they influence their galactic environments. Each new image, each refined measurement, brings us closer to understanding the physics at play in these extreme environments. From a fuzzy prediction to a sharp image, we are now in an era of precision black hole science, turning these mysterious phantoms into tangible objects of study. The darkness is finally coming into focus. The universe has a history book, and its pages are written in light. The farther we look into space, the further back in time we see. The James Webb Space Telescope is our most powerful time machine yet, designed to capture the faint, ancient light from the very first stars and galaxies. And in its deep gaze into the cosmic dawn, it has found something astonishing, something that challenges our understanding of how the universe grew up. It has found supermassive black holes that are far too big, far too early. They are cosmic giants in the nursery of the universe, existing just a few 100 million years after the Big Bang. This is a profound puzzle. Our traditional models for how supermassive black holes grow are slow and steady. A star-sized black hole forms, and over billions of years it gradually pulls in gas and merges with other black holes, slowly building up its mass. But these ancient black holes discovered by Webb simply didn't have enough time to grow that large. It is like finding a giant redwood tree that has grown to its full height in just a few years. It defies the known process. It suggests that something is missing from our story of cosmic evolution, that there must be another way to make a giant. Scientists are now scrambling to come up with new theories to explain these cosmic anomalies. Perhaps the very first stars were not just big, but gargantuan, hundreds of thousands of times the mass of our sun. When they died, they could have collapsed directly into intermediate mass black holes, giving them a significant head start. Another idea is that vast clouds of primordial gas in the dense early universe could have collapsed directly into a massive black hole, bypassing the star phase entirely. This direct collapse model could create the massive seeds needed to grow the giants Webb is now seeing. These discoveries are transforming our view of the early universe. It seems that black holes were not just a late-life consequence of cosmic evolution. They may have been fundamental architects from the very beginning. They might have acted as cosmic anchors, gathering matter around them and seeding the formation of the first galaxies. Instead of galaxies forming first and then growing black holes, perhaps the black holes came first and built the galaxies around them. The James Webb Space Telescope is not just finding black holes, it is finding the potential origin story of the grand cosmic structures we see today. For most of human history, our view of the universe was limited to what we could see with light. But in 2015, we grew a new sense. We learned to listen. We listened to the whisper of gravitational waves, ripples in the fabric of space-time itself, first predicted by Albert Einstein a century earlier. The Laser Interferometer Gravitational Wave Observatory, or LIGO, later joined by Virgo in Europe, detected these faint vibrations for the first time. The source of this cosmic tremor was an event of unimaginable violence. Two black holes, spiraling into each other and merging into one, hundreds of millions of light years away. It was a new way to sense the universe's most dramatic events. These ripples in space-time are a unique messenger. They travel across the cosmos completely unimpeded, carrying with them a pure story of the cataclysm that created them. By analyzing the frequency and amplitude of these waves, the chirp of the merger, scientists can deduce incredible details about their source. They can tell us the masses of the two black holes, how fast they were spinning, and the mass of the final black hole they created. It's kind of like hearing two bells ring and being able to describe their exact size, shape, and material just from the sound they make. This has opened a brand new field, gravitational wave astronomy. One of the most exciting quests for LIGO and Virgo is the search for a missing link in the black hole family intermediate mass black holes. We have found plenty of stellar mass black holes, up to a few dozen times the mass of the sun. We have also found supermassive ones, millions or billions of times our sun's mass. But the ones in between, from 100 to 100,000 solar masses, have been mysteriously elusive. Gravitational wave detectors are perfectly suited to find them, either by spotting their mergers with smaller black holes, or by catching the rare merger of two intermediates. Finding them would fill a critical gap in our understanding of how supermassive black holes grow. With every detection, we are building a census of the black hole population across the universe. We are learning how often they merge, where they live, and how they are distributed. Each event is a new data point, a new piece of the puzzle. Sometimes, the data reveals things we never expected, like mergers involving black holes in the mass gap where we thought they could not form. Gravitational waves are allowing us to observe the dark side of the universe directly, revealing a cosmos that is far more dynamic and violent than we ever knew. We are no longer just watching the universe, we are listening to its symphony. As we learn more about black holes, the questions we ask become even more profound. They push us to the very edge of what we know, forcing us to confront the deepest mysteries in physics. One of the most famous of these is the information paradox. According to quantum mechanics, information can never be truly destroyed. But if you throw something, like a book, into a black hole, it seems to vanish forever. Where does the information about its atoms and energy go? Does it escape somehow? Or is our understanding of physics incomplete? Solving this paradox is a key step toward the holy grail of modern physics, a theory of quantum gravity. The mysteries do not end there. Our universe is filled with an invisible substance called dark matter, which accounts for most of the matter in the cosmos. We know it's there because we can see its gravitational effects on stars and galaxies, but we have no idea what it is. One tantalizing possibility is that at least some of it could be made of primordial black holes. Black holes that formed in the chaotic moments, right after the Big Bang, not from stars. These could be wandering through the universe, completely invisible except for their gravity. Searching for these ancient relics is one of the great challenges for astronomers today. Black holes are the ultimate testing ground for our most fundamental theories. They are where Einstein's general relativity, which describes gravity on the largest scales, meets quantum mechanics, which governs the smaller scales. These two theories are incredibly successful on their own, but they do not work together. At the singularity inside a black hole, both theories must apply, yet they give us nonsensical answers. To understand what truly happens there, we need a unified theory, a theory of everything. By studying black holes, we are probing the very seams of reality, looking for clues that will lead us to that deeper truth. In the end, why should we care about these bizarre, distant objects? We care because the quest to understand them is fundamentally human. It's driven by the same curiosity that led our ancestors to look up at the stars and wonder. The pursuit of knowledge about black holes pushes our technology, inspires our young people, and expands our perspective on the universe and our place in it. They remind us that the cosmos is vast, mysterious, and full of wonders still waiting to be discovered. The story of black holes is our story, a story of looking into the deepest darkness to find the brightest light of understanding.